Hopefully in lesson 2, exercise 14b, you worked out that drawing a tangent against a curve is a better approximation of the slope of the curve at that point than drawing a chord, but it's still a fairly inaccurate way of doing things because it involves eyeballing the tangent. And depending on exactly where you draw the tangent, that's going to change the steepness of it, which then changes the steepness of the curve. In actual fact, the steepness of the curve doesn't change, so the fact that we've got this changing tangent is problematic. So the whole point of differential calculus, is working out what the exact slope is at an exact point without any estimation or eyeballing of tangents. Before we get into the calculus part of it, though, we have to investigate this idea of a limit because calculus involves dealing with limits. To investigate the limit, first we're going to have a look at the function x squared minus 4 divided by x minus 2. And the function is not defined at x equals 2. Why is that? You should recognize that when x equals 2, the denominator equals 0, which causes the function to be undefined. If we simplify the function like we've done here, we can do difference of two squares expansion in the numerator, and then what you see is that the factor of x minus 2 will cancel each other out and we're left with x plus 2. So this means that the function x squared minus 4 on x minus 2 looks like x plus 2, but we must keep in mind that x cannot equal 2. So when we graph it, we end up with this situation here. And you should be able to do this on your calculators as well. You might need to zoom right in, but what we end up with is what's called a point discontinuity. So instead of a function being defined for what looks like a line, like we saw with our reciprocal and rational functions, what we've got here is a discontinuous point that occurs actually in the line of the function. So if you graphed y equals x plus 2, it would look exactly the same as this, except that this one has the point discontinuity. And that's why it's got the open circle, because the function does not exist at that point. However, if we look at the graph here, you can see fairly easily that the coordinates of this point, if it existed, is 2, 4. If we look at the coordinates of the point when x equals 0, y equals 2. When x equals 1, y equals 3. So we've got this point 1, 3. The closer that we get to x equals 2, the closer we get to y equals 4. And that's when we're approaching from below. So x values lower than 2. We can't actually have an x value of 2 itself because the function doesn't exist at that point, which means we can't have a y value of 4 because the function doesn't exist for y equals 4. If we approach that point discontinuity from the other side, for example, over here when x equals 4, y equals 6. When x equals 3, y equals 5. And you can see that the closer we get to 4 from above, the closer we get to 2 from above, the closer we get to 4, the point discontinuity. But again, we never actually reach that point. And this is the concept of a limit. Very, very importantly, it doesn't matter whether x equals 2 is approached from above or from below, the same value of y equals 4 is approached. And this is the concept of a limit. So just in very quick contrast, and we'll have a look at this in an example below, not all functions approach the same value when you approach from above and below. And I'll make that a little bit more clear in example 3.2. The way that we express our limit is written like this. So it's the limit as x approaches 2 of f of x equals 4. So you can write it as f of x, or because it's better communication, we would write the limit as x approaches 2 of x squared minus 4 on x minus 2 equals 4. Notice that it doesn't mean that the function equals 4 at that point. What it means is, as you get closer and closer and closer to x equals 2, the value of the function gets closer and closer and closer to y equals 4. But because x can't actually equal 2, the function can't actually equal 4. If a function is continuous, as in it doesn't have a point discontinuity, then the value of the limit is the value of the function. So for example, looking at this same function here, x squared minus 4 on x minus 2, the limit as x approaches 3 is 5. And if we go back and have a look at the graph, and I'll get rid of all of these lines. Here's x equals 3. And as x gets closer and closer to 3, we can see that y gets closer and closer to 5. And in fact, the value of the limit is the value of the function, because when x equals 3, the function is continuous, as in it is defined at that point. There's a more formal definition of limits there. And in the next example, we'll have a look at what happens when limits don't exist.